Hello, welcome to lecture 13 of Elec Eng 2CI5. In this lecture, I will address the concept of superposition. It's a very important concept in analyzing linear electric circuits. So we'll define what is the condition for a circuit to be linear and how we can use superposition to simplify the analysis of the circuits. All the circuits that we discuss in 2CI5 are linear circuits, whether even they include capacitors and inductors and so on. The reason for that is that the basic relationship governing every element is linear. For example, for the case of the resistor, we knew the equation governing the resistor is V is equal to IR. So the current and the voltage grow linearly together through the scale factor, which is resistance. Later, when we discuss inductances, you will know that the flux through a linear inductor is equal to L, the inductance multiplied by the current through the inductor. So this is also another linear relationship, and L here is the inductance, which is a constant of proportionality. And when we study capacitors, you will know that the equation governing a linear capacitor, Q, we can simply write it here as Q equal to CV. So the charge stored in the capacitor is linearly proportional to the voltage across the capacitor, and the constant of proportionality is C. So all these are linear components. The components themselves are given by linear equations. So when the current will increase, the voltage will have to increase in a linear way. The same thing when the current is increased here, the flux will increase. When the current increases, the charge will increase, and so on. Linear circuits satisfy two conditions. One called additivity, and the other one called scaling or homogeneity. Actually, this called here is called additivity here, and this one is called scaling or homogeneity. Okay, what's happening here if you have a circuit and it creates an output? So the input to the circuit, we call it X. It can be the value of a voltage source. The output is f of X. It can be the current in one of the branches. It can be the voltage across one of the other branches. So if you scale up the excitation by a factor alpha, if alpha is 10, means you multiply the excitation by 10. This means that the output will also be scaled by 10, by the same factor. And if you have two different inputs, x1 and x2, x1, if you have your source, it has a value x1, it will give you an output, which is f of x1. If your source is x2, it gives you a value of f of x2. If you sum the two excitations, so if you have a voltage source of 4 volts and this one is 5 volts, so if you apply a voltage source of 9 volts, the output from the circuit will be the sum obtained from the 4 volts case and the 5 volts case. This is a condition of additivity. These are the two conditions that classify linearity. So I will start in the next slide to show you two definitions of linearity. One of them uses this condition, the other one using another way of defining it. So we say that a model y is equal to t of x. X here is our input. It can be the value of a voltage source or a current source. Y is our output. It can be the value of the current flowing through a branch, or the voltage across a branch, or some other quantity. And t here is the calculation that you use to convert your voltage source or current source into the output. We see that this model is linear if and only if. This here IFF means if and only if. Means that if this condition is satisfied, this condition here, then the system is linear. And if the system is linear, this condition must be satisfied. So it's a two-directional logic. So if the system is linear, this condition must be satisfied, and if this system is satisfied, this condition the system must be linear. This is a bi-directional argument, and you use for this if and only if. The people who studied algebra will know this is used very often in algebra. So what's happening here? If you have a circuit, you put it an input x1, it creates an output t of x1. You put an input x2, it creates an output t of x2. So if you put an input which is a1 x1 plus a2 x2, you scale the first input by a constant a1, you scale the second input by a constant a2, then the output you are going to be getting is a1 t of x1 plus a2 t of x2. And this is for all possible inputs x1, x2, and for all possible scalar coefficients a1 and a2. Let's take a look at what does this mean. I choose for you a very simple circuit. It's a voltage divider. I have here an input voltage, an independent voltage source, and I have a voltage divider, and this is my output. So this is X and this is Y. Okay? So you can see the relationship is that Y is equal to 2 over 3X. This is the relationship in this voltage divider. X is my source and Y is the voltage I measure at the output. So here Y is equal to T of X is equal to 2 over 3X. And X is the value of this voltage. When you put here 3 volts, it means that you give X the value of 3. So X1 is equal to 3. And in that case, the output of the circuit T of X1 is equal to 2. Okay? Now let's scale this input by a factor of 2. So I selected the coefficient of 2. So now the input is equal to 2 multiplying X1. So I scaled the input up by a factor of 2. So when you have 6 at the input, okay, the output now becomes, if you do the calculation, the output now becomes 2 over 3 multiplying 6. So this is going to give you here, this one here is going to give you 4 volts. So between here and here, you're going to measure 4 volts. So you scaled the input by a factor of 2. The output was also scaled by a factor of 2. This is the scaling condition for linearity. Okay. Now if I select another input and this input is 12 volts, the output here will be equal to 8 volts because 8 volts is equal to 12 multiplying 2 over 2k over 2k plus 1k. So if x2 is 12, T of x2, which is the output voltage, is equal to 8. So here the scale factor is 2 over 3. If I scale this one here by 2 over 3, then I get an input which is 8 only. Okay? And this will result in the output also be scaled by a factor of 2 over 3. So you multiply 8 volts by 2 over 3, you get 16 over 3. This is not written here, but this is what you have. This will be 16 over 3 volts. Okay? Now, so let's see how do we apply this equation. We applied x1, which is 3 volts. We got T of x1, which is equal to 2 volts. We applied x2, which is 12 volts. We got T of x2, which is equal to 8 volts. If we form a combination, which is A1 x1 plus A2 x2, A1 x1 is 6 here, 2 multiplying 3. A2 x2 is 8, which is 2 over 3 multiplying 12. If you sum these two, 6 plus 8 will give you 14. Then the output the system will give you for an input which has a value of 14 is equal to 2 multiplying 2, which is T of x1, plus 2 over 3 multiplying the output is corresponding to the 12, which is 8. And indeed, if you do that, you'll get that this one here will be equal to 2 by 2 will give you 4. This one here will give you 2 over 3 multiplying 8. So give you 16 over 3 plus 4 will give you 28 over 3. And indeed, if you put an input here of 14, the output will be 14 multiplied by 2 over 3 will give you 28 over 3. Okay, so I tried to give you the same thing in numbers here. So this one here will give you 28 over 3. If you select A1 to be 2, X1 to be 3, A2 to be 2 over 3, X2 to be 12. Okay, and in that case the new input here, this combined input is equal to 14 volts. Okay, this is a condition of linearity. Another definition of linearity is the one we talked about earlier. You apply an input x1, you get an output T of x1. You apply an input x2, you give it an output T of x2. What if you want to apply an input T of x1 plus x2? What you'll have to do, I'm gonna go to the end here. So if this distance here is equal to x1, I'm gonna be copying it here. Okay, so this is now is x1, and this whole distance now becomes x1 plus x2. Okay, if you try to see the output that this circuit will create, okay, you'll see that the output is T of x2 that you have here. This is T of x2, and you added to it T of x1 as well. So if the input is x1 plus x2, the output of the circuit will be T of x1, which is this one, plus T of x2. And of course, this condition is saying the whole thing scales linearly as shown here. And by the way, this linear scaling means that it has to go through the input. through the origin. So if you put x equal to 0, means that the coefficient is 0, must get 0 at the output. Okay, so if you put a equal to 0, the input, the output of the system corresponding to 0 will be equal to 0 multiplying by this number, so it's equal to 0. So this is why any linear circuit must go through the origin. This simply saying when you don't have an excitation, you don't have a response. If you don't have an input voltage at the an independent voltage source and the input, you don't get any current at the output. This is what this means. Okay, the previous part was theoretical, so let's now see how we can use linearity to solve a circuit. We have a circuit here, we have a current source 12 milliampere, we have a number of resistors here, and we'd like to calculate the current I naught. Of course, we can do a sequence of current divisions, but what we can do it in the opposite direction. Let's assume that I naught here is already 1 milliampere, and try to see what is the excitation that will give me this current of 1 milliampere. So what we are doing now, we are going to assume, and this is really what we are doing in this question, we're going to assume that that T of x1, the output already coming from the circuit, so T of x1 will be equal to 1 milliampere, okay? And then we'll try to figure out what is x1. So this is what we have. The output here, y or T of x, is I naught. The input is this source, okay? I'm going to assume now that I have an output of 1 milliampere, and I will walk this back to see what is the input that's going to give me this current. Okay, so let's see. If I have 1 milliampere here, this is 4K in parallel with 4K. This is 1 milliampere, so this also must be 1 milliampere, because these two are in parallel. This 1 milliampere and this 1 milliampere, okay? So these two are 2 milliamperes. Remember, this resistance is 1/2 the value of this branch and this branch. So this one will give double the current. So if this is 1 milliampere and this 1 milliampere, this will be 2 milliampere. So the total current flowing here will be 4 milliampere. Okay? Okay, so this one step forward. If this is 4 milliampere, okay, the parallel combination of all these three will give me 1K. So the equivalent resistance in this branch is 3K. Okay, you have here 4 milliampere flowing in a 3K, which is in parallel with 2K. So I can get the current here. The current here will be equal to 3/2 multiplying by 4 milliampere. Okay, 3/2 multiplied by 4 will give you 6 milliampere. So the input current here will be equal to 10 milliampere. So 10 milliampere at the input will give you 1 milliampere at the output. So when you put x equal to 10 milliampere, you get T of x equal to 1 milliampere. So what is the output corresponding to 12 milliampere? Okay, we apply linearity. We see the thing scales. When you scale up the input, you scale up the output in the same way. Let's see how this is done in the next slide. Okay, let's go over this again one more time. Of course, you can solve the circuit in the forward way. You can divide this current into 2, find the total input resistance seen from this side in the same way we did before, divide this current into 2, and then divide this current into 3. You'll be able to get I naught. This is one way of doing it. But I will not do that. I will assume that I naught is 1 milliampere. Okay? If this is 1 milliampere, this is 4K in parallel with 4K, then the current going through here, I1, must also be equal to 1 milliampere. Because these are this resistance, and this resistance are in parallel. If this one gets 1 milliampere, then this 1 milliampere. But this 2 kilo ohm is 1/2 the value of this one and this one. If the resistance value is 1/2, it gets double the current. So if this is 1 milliampere and this 1 milliampere, and they are in parallel with the 2 kilo ohm, so the 2 kilo ohm will get 2 milliampere. So I2 is equal to 2 milliampere. I3, the current flowing here, is equal to I2 plus 1 milliampere plus 1 milliampere, so it will be equal to 4 milliampere. Okay? Now, if you try to find the parallel combination of all three, 4 in parallel with 4 will give you 2, 2 in parallel with 2 will give you 1. So these three resistances are equivalent to one resistance of value 1 kilo ohm. So this is 3 kilo ohm here. So you have a current I3, which is 4 milliampere, flowing in a 3 kilo ohm. What is the current I4 flowing in the parallel 2 kilo ohm? Okay, so this is really what, this is how I can draw it here, just to see what's happening. I have 3K this way, and I have 2K this way. Okay, this one here is I3, and this one here is I4. I want to get I4. Of course, the smallest resistance get a higher current. If I3 is equal to 4 milliampere, this is 2K, this is 3K, I can simply say that I4 is equal to 3 over 2 multiplying I3. So if you do that, this expression here, this is from current division rules, I get 6 milliampere. This is 4 milliampere, this is 6 milliampere, so the current input is equal to 10 milliampere. So what's happening here? I assume the output Y of X to be equal to 1 milliampere. I was able to get X, which is the input current, the value of this current source, to be equal to 10. So if the input is equal to 12, what is the output? If you scale the 10, you make it 12, this means you multiplied it by 1.2. But if you scale the input by 1.2, then the output will also be scaled by 1.2. So this means that I naught must be equal to 1.2 milliampere. Okay? Because it's a linear relationship, it's a linear system. So 1 milliampere at the output corresponds to 10 milliampere at 10 milliampere at the input. So what corresponds to 12 milliampere at the input? What is the corresponding output? Well, you apply linearity. If this was 10 milliampere, I got 1 milliampere. If you make this one 12 milliampere, this means use the scale factor of 1.2. Then the output will also be scaled by 1.2. So multiply by 1 milliampere, 1.2, you get 1.2 milliampere. Okay, so now we know, and of course you are welcome to repeat these same steps using the way we did in the lecture. Combine all the three, combine this one, get one equivalent resistance, use current division. You will see that the current flowing here is equal to 4.8 milliampere. You get 1.2 milliampere here, 1.2 milliampere here, and 2.4 milliampere here. So I didn't make this verification. Okay, how do you use superposition in analyzing circuits? Superposition is really a statement of linearity. It is simply telling you that if you have multiple sources, multiple independent sources in your circuit, then the current and voltages everywhere is a result of all of them. But the circuit is linear. So what I can do, I can handle one source at a time and remove the other sources. This is really the basic concept. Try to reduce the problem to just handling one source at a time. Now, it should be clear in our minds that a current source gives a constant current. If you want to remove that current source, you have to make the current equal to 0. So for example, if I have a current source flowing in one branch, and this current is equal to 3 ampere. Okay? If I want to remove that current source, I want to remove it from the circuit, I must make the current flowing in this branch equal to 0. To make the current flowing in this branch equal to 0, we make this branch open circuit. Okay? So what we are going to be doing, in order to eliminate a current source, we are going to be making it open circuit. Voltage source is the opposite. If you have a voltage source connected in a certain branch, it gives you a voltage of 5 volts. If you want to convert this voltage at the input to 0, what you do, you create a short circuit, because a short circuit has 0 voltage across it. Okay? So now every voltage source we want to eliminate, we have to convert to a short circuit. Every current source we want to eliminate, we have to convert to open circuit. Notice that this applies only to independent sources. Why? Because independent sources are actual sources, while dependent sources, as we explained at the beginning of the course, represent transistors, represent amplifiers. They are really components. They are not really sources. Okay? So you cannot use this rule to eliminate dependent sources. You only eliminate independent sources. Okay, so this is how superposition is going to be done. You have a number of independent sources. You solve the circuit multiple times, each time for only when only one source is present, and then you remove the other sources. You move every voltage source short circuit, make every other voltage source short circuit. Okay, so as shown here, you short circuited, and you make every current source open circuit, and then you apply superposition to get the value of the voltages and currents everywhere. Remember, if you have a current in a branch, this current is due to all the sources that you have. So you get the current in this branch due to the first source, and then the current in this branch due to the second source, and then due to the third source, and so on. So you do it all of them one by one, and then you sum the result. Superposition can be illustrated through examples. So let's take a look here at a circuit. This circuit has three independent sources. Okay, we have a current source 4 milliampere, a voltage source 6 volts, a voltage source 12 volts, and we would like to calculate the output. Okay, the output voltage here is due to the current flowing in this resistor, but this current is due to all three sources. This is a linear circuit, so I can apply superposition. I can handle one source at a time. So I'm gonna first keep the 6 volts and then remove this one, make it short circuit, and then make this one open circuit, and then calculate the output due to this source only. And then I'm gonna keep this one alone, and I will make this one short circuit, I will make this one open circuit, and calculate the output due to this source alone. And then I will make this one short circuit and make this one short circuit, and keep only this one and calculate the output due to this source alone. And then we sum all three contributions, V output 1, V output 2, V output 3. I give them the label 1, 2, and 3 depending on the source. So let's do that first. Let's eliminate this one, make it short circuit, and make this one open circuit. You will have to redraw the circuit every time. So now what I did, I removed the current source. The current source used to be used to be here between these two terminals. Okay, the current source is not there anymore. It's open circuit. There was a voltage source here. It is gone. I have only this source here. So I'm now calculating what I call V output 1. V output 1 is the component of the output voltage V naught due to the first source. It's very simple to see in this circuit. Once you have built this circuit, you have to analyze it. You have 1K in parallel with 1K, so this is going to give you half K. Okay, so the circuit now looks more simplified this way. This looks like a voltage divider. You have 6 volts and you have 2 resistances in parallel. But remember the polarity of the drop, positive, negative, positive, negative. Then the output voltage you're going to get here will be negative. Okay, so if you want to calculate V output 1, the voltage here, remember there is a current, the same currents flowing in these two resistors. Then there will be some drop here and some drop here. But notice the polarity of the required V output. The voltage we calculate from 6 volts will have an opposite polarity. Okay, so I can simply say that V output 1, the output voltage V naught due to the first source, which is 6 volts, is equal to minus 6 multiplying 0.5 over 0.5 plus 2. It's a voltage divider between 0.5 and the 2 kilo ohm. Okay, 0.5 kilo ohm and 2 kilo ohm. If you do that, you get that the output voltage here due to this source is minus 1.2 volts, and it has to be very clear in your minds why do we have this negative sign, because the polarity of this source get positive negative and then positive negative, okay, which is the opposite to the polarity of the V output. Okay, we have to observe polarities and directions of currents when we are doing superposition. Now we repeat the analysis again. We keep only the 12 volt source, we shorted the other voltage source, and we removed the current source. We went open circuit. Okay, now this is how the circuit looks like. Of course I have 2 kilo ohm in parallel with 1 kilo ohm here. These two combined will be equal to 2 over 3 kilo ohm. So the circuit, this is how the circuit now looks like. 12 volts here and you have these two in series, so this now acts as a voltage divider again. But this one here is positive negative, so it is the same polarity as that of the source. So I can simply say that V output 2, which is the output voltage due to the second source, is equal to 2 kilo ohm multiplying 12 volts here that you have, 12 volts multiplying 1 kilo ohm over 1 kilo ohm plus 2 over 3 kilo ohm. It's a voltage division. And if you do that, you get 7.2 volts. Now the last step is to analyze the circuit for the current source while shorting the two voltage sources. So this is what we did here. I shorted the first voltage source. This is the 12 volts used to be here, 6 volts used to be here. They are both shorted. You have only the current source. Of course, in this case, if you see a current flowing here, this current will continue this way because it's a short circuit between here and here. So this bar, there is no current flowing in this part, in this lower resistance. This will give me one resistance only, which is 2 in parallel with half kilo ohm. But there is no current flowing here really. the current will flow in the source like that, and V output 3 will be equal to 0. So the sum of all three voltages will be equal to V output 3, which is the output voltage due to the third source, plus V output 2 due to the second source, plus V output 1. This will give you 6 volts. So we now use superposition to analyze the circuit with multiple sources. Of course, we could have done it using nodal analysis. We could have done it using loop analysis. We should be able to get exactly the same answer. I did a simple check in this circuit to make sure that I can apply, I got the same answer. So what I did, I applied nodal analysis. If you notice, I have here one node, second, third, fourth, fifth. So I have 5 nodes. I have 2 voltage sources. When a voltage source connects to 2 nodes like this, it creates difficulty and give us one more piece of information. One more piece of information here is that V3 is equal to V1 plus 6 volts. And this one gives us one more piece of information that V4 is equal to V1 relative to 12 plus 12 volts. So we can eliminate 2 of the unknowns. So we have only here V1 and V2 of the unknowns. Now, if you want to apply KCL here, you will not be able to, because you have this voltage source. So you have to go and do super node. But here there is something interesting. If you try to do super node here, also it's not going to work. Why? Because this super node is also connected to another voltage source. So what you have to do in this example, and this is what I did, you have to build a super node that will surround both voltage sources. I found this very interesting, and I wrote the expression here. So I have how many currents flowing out? 1 current flowing out, second current flowing out, third current flowing out, fourth, fifth, and sixth. And you can write all these currents in terms of V1 and V2. Okay? Because remember, V3 is V1 plus 6, V4 is V1 plus 12. And you have to write KCL here as well. So you obtain 2 equations and 2 unknowns. One equation here from the super node for V1, one equation here from this node here. So you have 2 equations, 2 unknowns, you solve for them. I did that already. I'm going to give you the final answer, but you have to check it yourself. If you do the solution, you will get that V1 is equal to minus 6 volts. So V4, which is V output we're looking for, will be equal to minus 6 plus 12, which is equal to 6 volts. So this is the same number we calculated using superposition. I'm leaving it for you as an exercise, and I found this very interesting that you try to build a super node around the voltage source and still doesn't work, because you have another voltage source connected to that super node. Then you have to make the super node even bigger. Okay, so please try to sum all 6 currents flowing out, okay, and prove and set their sum equal to 0 to obtain one equation between V1 and V2. Second equation can be obtained by writing KCL at this node. Okay, let's have one more example. So this is a circuit. But this one has dependent source. So we have one independent current source, one independent voltage source, and one current dependent current source. So the current here is 4I, and the I is the current in this branch. We have to apply superposition the same way we do it. No difference. Remember, we have to analyze the circuit once when the 12 volts is there and this one is open circuit, and the other time when the 12 volts short circuit and this one is only present. And then we sum the current going through the 4 ohm for both of them, and this will give us the total current. Dependent current sources, they represent actual components in your circuit. They are not really true sources. They represent the amplifiers, represent transistors, they represent the op amps. So you cannot really remove them. You have to keep the circuit as it is. Okay, so what I did here, I removed the current source. The current source has been removed, it's open circuit. I kept the voltage source. I have now to find the current here due to 4 ohm. I have only one node and ground here in this circuit. So the easiest way to do it is to simply apply nodal analysis. So you simply say the current flowing out, so V1 minus 12 over 1 ohm plus V1 over 3 ohm plus 4I is equal to 0, okay? So this is what you write. And this current, I took it here as flowing in as minus I. This current flowing in is 12 minus V1 over 1, okay? So you obtain one equation V1. You solve for V1. It's very simple. It's one node because the second node is ground. You solve, you obtain V1 equal to 3.5 volts. If I have V1 at 13.5 volts, I can get I, because I is 12 minus 13.5 divided by 1 ohm. So you are able to get I here is equal to minus 1.5 ampere. So the current flowing here, I call it I4 ohm dash. I4 ohm dash means the 4 ohm current due to the first source is equal to 4I. It's flowing this way, but I is minus 1.5, so the current here is minus 6 ampere flowing in this direction. So I4 ohm dash, the 4 ohm resistance to the first source, is equal to minus 6 ampere, and it's flowing in this direction. Direction does matter. You have to take this into account. It's minus 6 ampere flowing in this direction. Okay, we repeat the circuit analysis. Now we get rid of the voltage source we shorted out. We keep the current source. Again, this circuit has only one loop, one node. This is one node here. These are all shorted. And the second node is ground. Okay, so the easiest way to solve it, don't please treat it as 3 loops. Don't apply loop analysis here, because loop analysis will give you one equation, a second equation, a third equation. Why would you do that when you have only one node here? So I applied KCL here. So Vt, the sum of all currents flowing out is equal to 0. So 4I plus V2 over 3 minus 5 ampere plus V2 over 1 will be equal to 0. This is the equation here. Okay, I can count I as flowing in, but I give it a negative sign. It doesn't really make any difference. I have to get rid of I. Every time I have a dependent parameter, I have to get rid of it. This current I is equal to 0 minus V2 over 1 ohm. I call this voltage here V2, by the way. So if I can get rid of I and replace it by minus V2. If you sum all the coefficients, you get this equation for V2. I is gone. 8 over 3 V2 is equal to minus 5, or that V2 is minus 15 over 8, which is minus 1.875. So the current flowing here, okay, so the current I here, I call it here I1. My apologies for this. This is really I, is not I1. This is I. This current here is 0 minus V2 divided by 1 ohm. So it is 0 minus 1.875 divided by 1. So you get 1.875. You multiply it by 4, you get 7.5 ampere. So you have 7.5 ampere flowing in this circuit in the 4 ohm resistor. The other one gave us minus 6 ampere. So the total current flowing in the 4 ohm resistor, we have two currents. One of them is 7 ampere flowing this, 7.5 flowing this way, and minus 6 flowing this way. If you sum them, you get that the net current is 1.5 flowing in this way. Okay, flowing in the clockwise direction, 1.5 ampere. You could of course use nodal. You can verify your answer by applying nodal analysis to the original circuit that has two sources. I did that. I'm showing you the answer just to be able to check it, that the voltage here will be equal to 93 over 8, and the current I for the complete circuit where you have two sources will be 3 over 8, and when you multiply this by 4, you get the current flowing here will be equal to 3 over 2, which is 1.5 ampere, which is the same answer we got from superposition. So right now you should feel that you have multiple tools really to solve any circuit. You can use loop analysis, you can use nodal analysis, you can use superposition. Okay, and of course they are going to give you the same voltages, the same currents around the branches and everywhere in the circuit.